Welcome to the channel. This is Math Whimsy and my name is Lisa. I've been a long-time math teacher and I'm ready to solve some problems. Here's the plan for attack for today. Number one, what's a parabola? Where do they show up in nature? Why are they significant? Why should we even care about them? And then what are the main features of a parabola, also known as a quadratic function? Number two, how do we manipulate the shape of a parabola? So once we've established what a parabola is and how it works, we're going to learn how to use the equation of a quadratic function to manipulate the shape of a parabola. And then number three, how do I use what I know about parabolas and apply them to real-world concepts? So we have tons of parabolas that we see all around us. How do I map them? Meaning, how do I apply the equation to the shape of a parabola, to the shape of a ball flying through the air? And of course, before we begin, there is the matter of roll call. Your attendance question for today, since we're talking about projectile motion, in your opinion, what do you think would be the most satisfying fruit to throw? Let's get started. So, parabolas, the most intuitive understanding that we have about them is projectile motion. That is, the path something takes as it flies through the air. And it's so intuitive that at a really young age, we can start to predict where something is going to land after it's been tossed. It's this amazing phenomenon that at such a young age, we already have the mathematical knowledge in our brains to make these micro calculations and predictions. But if we want to send a rocket to space, we're going to have to get a little bit more technical. Well, as most equations, we're going to start with a y equals. After the equal sign, we place an x. The thing that draws the parabola is this little guy. It's the squared, which means we're multiplying the x value by itself. We're going to start replacing x with different numerical values, for example, 0, and then calculating what that equals for the y. So 0 squared, 0 times 0 is 0, and we have our first coordinate. So our first coordinate is going to get placed right there. That point actually has some significance, and we'll come back to that later. If I plug in the value 1, 1 squared is 1, and we have our next coordinate. 2 squared is 4, and 3 squared is 9. As you can see, the points, the dots, are getting further and further away from each other as we move to the right. And this actually creates a really nice curve. We have this empty space on the left-hand side of the graph, and that's because we haven't tried to use negative x values. Before we do that, I need to establish a ground rule here. Because the little squared is the meat of the equation, it's what gives the parabola its shape, we need to make sure that whatever number we replace x with is contained within the square. Containment, using brackets. And now we have the freedom to put whatever value inside without making any calculation errors. Starting with the number -1. -1 squared, -1 times -1, a 1. And so we have an equation where our x is -1 and our y is 1. You'll notice there's symmetry. We have a similar point on the other side. Let's see if that's the case for the others. -2 squared, +4. So once again, -2, +4. There's that symmetry of yours. -3 squared is 9. Finishing to fit onto our graph that we've drawn. So the basics of a parabola, how to establish it using equations. You can also do this using a table of values, also known as a t-chart. There are 3 more concepts that we're going to cover so that we have the vocabulary as we move forward. The first one is this important significant point. I pointed this out earlier. This point right here is the only one that doesn't have a twin. It doesn't pair off compared to the other points. So this point right here is where everything grows from, and we call this point the vertex. And right now, for the basic equation, y equals x squared, the vertex is at 0, 0. Going straight through the vertex, cutting the parabola in half, is this perfect line of symmetry. And we call this the axis of symmetry. So this vertical line has the equation x equals 0 because it goes through the 0 value for x. The final feature is related to the direction of opening. Right now, we would say that the graph or the parabola is concave up, or you can just say simply opens up, meaning the arrows on the ends of the parabola point up. All right, so now that we've established the basic shape of a parabola, we know that the y, the x, and the squared are required pieces in order to draw this specific shape. But how do I get it to map the path of the ball? Because that parabola is upside down. So that brings us to the 3 transformations for a parabola. We can move a parabola up and down. We can move a parabola left and right. And we can also stretch a parabola, having it go very, very narrow, quite wide, and even flipping upside down. You'll notice that we still have the original y equals x surrounded by brackets and the squared. Those are crucial in order to create the shape of a parabola. What's new here are the 3 new variables that would all be replaced by numbers, and each one of these numbers changes the shape or the location of the parabola. The a value is the only number that's being multiplied. The a value is called the stretch and the reflection. The h and the v are added or subtracted values. H is inside of the brackets with x, and I'm using the variable h to represent a horizontal change. So h for horizontal, although a lot of times other textbooks might use a p. The letter doesn't matter, the location matters. H is inside of the brackets with x. H is also affected by that squared. So H is the horizontal shift, left to right, and we're going to come back to this because H has an extra rule. V stands for vertical. V is the vertical shift, so V will move the parabola up or down. Now there is an added little asterisk above the H because H works in the opposite that you would expect it to. H is counterintuitive, meaning let's say I add the number 4 in the spot for V, that will move my parabola up 4 spaces. However, if I was to do the same thing to the horizontal value, you would expect this number to cause the parabola to shift to the right 4 spaces, but in fact, it causes it to shift to the left 4 spaces. So that's the counterintuitive piece. It's going to move in the opposite direction than what the sign indicates. So if it's a positive, it moves left. If it's negative, it moves right. To model a parabola, we're going to kick a soccer ball and then map out the flight of that ball. To get started, we're going to go to desmos.com and we're going to select Open Graphing Calculator. We can import an image by hitting the plus icon in the top left-hand corner, and I'm going to import the image of the soccer ball kick. I've selected the metric measurements, but all of these images with metric and imperial measurements are available for download on my website. Now, this image is not centered very nicely on the graph. We have a measurement of 140 centimeters, and I would like that to be reflected in the numbers on the axes. So, as a reference, I'm going to type y equals 140, and that's going to create a nice horizontal line for me to follow as a guide to try to fit my image to. The next step is a little bit finicky, so bear with me. You're going to enlarge and move your image until your measurement fits nicely where you want it to go. I would also like my ground to be right up against the x-axis. One thing to watch out for, these blue circles that are in the center of the edges of the image will distort the aspect ratio. Since we only have one measurement, by pulling on those circles, we're going to completely distort the image, and so the horizontal measurements won't be as accurate. So make sure that you're only changing the picture by the corners. Now that I'm happy with the way that my picture fits on my graph, I can go ahead and delete that reference line. We can start planning our equation for the parabola. We need two coordinates, two significant coordinates. Coordinate number 1 is the vertex. And the vertex in this case is right at the highest point. Since I want my parabola to cut straight through the center of all of the soccer balls, I'm looking for a vertex that's sitting somewhere right in the middle right here. So that coordinate for me looks like 245 and 220. So I'm going to graph that as a coordinate, and I'm going to label it vertex. Now, in order to determine the A value, I need a secondary coordinate. It can be any one of these soccer balls or at the center of any one of these soccer balls. I'm going to go ahead and choose this very bottom one just as it's hitting the ground. To me, it looks like the center of this soccer ball is sitting about there, so 380 and 7. Now that I've established the coordinates, it's time to do some math. So here's what we have so far. We have a vertex, and we have a secondary point. The equation of a parabola is, where you'll recall that the y, the x, and the squared, along with the brackets, are the meat of the equation. The a, the h, and the v are all values that are going to be replaced with numbers to help us manipulate its shape. We're going to start with the h and the v. The h tells us where the parabola moves left or right. The v determines where the parabola moves up or down, specifically the vertex. If you recall, our vertex of the original parabola is at 0, 0. So how do we pick that vertex up and move it to where we want it now? To the right 245 spaces and up 220 spaces. If I want to move an object up 220 spaces, I'm going to replace the v value with that number. So since this is positive 220, we're going to replace v with positive 220. If you recall, the h value comes with a little counterintuitive rule, so it actually works in the opposite way that you would expect it to. Since we want to move our parabola to the right 245 spaces, we're going to change our h value to be negative 245. Last but not least is the a value. Now the a value is one of the trickiest parts to get, and that's why we need our secondary point. In order to calculate the a value, we are going to use these values, 380 for x and 7 for y, and we're going to plug them into our equation for x and y, and we're going to solve for a. So a will be our last unknown in the equation to solve for. Replacing y with the number 7, x with a number 380. Starting with mathing the things that are mathable, we're going to go ahead and math that part. So 7 equals a. Now, following basic algebra steps, all right, now that we've calculated our a value, we're going to use our a value and plug it back into the full form of the equation. We're going to return x and y back to their original status. We just replace them with numbers to help us calculate a value. And once we're done that, we have the equation that we need. Now that we've done our equation, it's time to test it out. Y equals negative 71 over 6,075. I am choosing to use the fraction version for my a value rather than the decimal value. It really doesn't matter at this point. Just use about 3 or 4 significant digits. X minus 245 squared. Remember, we need that because that's the key to the shape. Plus 220. Now the red line goes perfectly through the vertex and the coordinate that we've determined. It looks like it goes through the center of most of the soccer balls and gets a little bit wonky on the left-hand side. And that's probably because I had to
estimate where the vertex was, I could have probably put it a little lower and a little to the left. But because the line does cut through the soccer balls, I'm happy with it. We're going to do one last thing, and this one's totally optional. I would like to restrict my shape because the shape does go on forever. And since this is a model of a projectile, I would like the shape to begin at the center of the soccer ball here and to end on the ground right here. So the center of the soccer ball here is about 131 centimeters for the x value, and the ground right here is at 382 centimeters. So in the same line as our equation, we're going to set a domain. And if you're interested on how domain and range works, stay tuned for another video. Start any domain and range with curly brackets. 131 is our left wall, x, so you can see that the shape is now restricted, less than or equal to 382. And it stops right when it hits the ground right there.
Whew. All right, what a challenge. What have we learned? Number one, you've already got the mathematics for parabolas in your brain. If you've ever participated in any kind of ball sports or thrown or caught anything, you can already do it. We learned about the basic form of a parabola, the basic shape, why it has the shape that it does, and what are the key features of its equation. We learned about vertex form and how to use the vertex form to manipulate the shape of a parabola. And we also learned how to apply that vertex form to model the path of a projectile as it's flying through the air. The images that I used in this are available for download. There are measurements that are available in metric, so centimeters, or imperial in inches. I also have another different shaped parabola with the soccer ball kick, and I also have a few water hose images as well that you could use. Take a stab at it and show me what you get. Don't forget to answer the attendance question in the comments below, and I'll see you next time. Bye!